Japan is $12 billion deep into a project that sounds like a contradiction. They are building a tunnel to protect Tokyo from earthquakes, and they are digging it through the softest, most unstable ground on the planet. You build underground to escape the shaking above, but if the ground turns to liquid, the tunnel becomes a death trap. That is the paradox at the heart of this shield. The Kobe earthquake in 1995 taught Japan that buried concrete does not survive a major quake by being strong. It survives by moving with the ground. The Science Direct report from the Soil Dynamics and Earthquake Engineering Journal documented the damage from that event. Tunnels cracked, stations collapsed. The ground didn't just shake, it flowed. You are sitting on top of a city built on a river delta. Tokyo sits on layers of alluvial clay, soft sand, and ancient seabed. The water table is barely 3 meters down in most places. Digging through that is not like mining granite. It is like trying to carve a tunnel through a wet sponge that someone keeps squeezing. The seismic network that Japan built after 2011 uses 186 observatories connected by more than 3,500 miles of fiber optic cable. It can detect a tremor before the P wave reaches the surface. But detection is not protection. A warning arrives 15 seconds before the shaking. 15 seconds is not enough time to evacuate a city. So they are building a tunnel that absorbs the energy instead. But there is a problem. A shield tunnel works by pushing prefabricated concrete rings into the earth as a machine eats the ground ahead. The machine, a tunnel boring machine that weighs several thousand tons, advances meter by meter, sealing the void behind it with those rings. In soft ground, the risk is not overhead collapse. It is the face. When the cutter head opens a hole in saturated soil, the pressure difference can turn the tunnel into a geyser. Here is what nobody tells you about drilling through an active seismic zone. The fault lines are not static. They are breathing. The Pacific plate is subsiding under the Philippine sea plate at a rate of several centimeters per year. That means the ground is constantly under strain. A tunnel that is rigid will snap. A tunnel that is flexible will deform. The Japanese approach, documented in the Yashiro paper from the Soils and Foundations Journal, uses something called earthquake-resistant segmental lining. The rings are bolted, but not locked. They can shift. They are designed to crack in controlled places. At 30 meters below the surface, the water pressure is already 3 atmospheres. At 60 meters, it climbs to 6. The tunnel has to be sealed at every joint. The gaskets are made of a compressed rubber compound that swells when it contacts water. If the gasket fails, the tunnel does not flood slowly. It fills in minutes. Straight from the Japan Society of Civil Engineers case studies, a single gasket failure in a deep shield tunnel can allow over 100 cubic meters of water per second into the bore. That is a swimming pool every minute. A single gasket failure, a swimming pool every minute. The engineers test each joint 3 times before it enters the ground. If you want to see how they build a tunnel that can survive that, subscribe and follow the descent. And in the comments, type swimming pool, because that image stays with you. The $12 billion is not just for the tunnel itself. It covers the 23 access shafts, the underground pump stations, the continuous monitoring systems that check for millimeter-scale shifts in real time, and the redundant power grid that keeps those systems running when the main grid fails. The post-2011 seawall program alone cost $12 billion for 400 kilometers of coastal defenses that rise to 14.7 meters. This tunnel is proportionally more expensive because it is being built through an urbanized seabed. But there is a catch. The same flexibility that protects the tunnel during an earthquake also makes it harder to navigate during regular operation. The segments are not perfectly aligned. They have intentional gaps that allow movement. Those gaps collect silt. Over time, the silt hardens and the tunnel loses its ability to flex. The maintenance cycle is brutal. Every 10 years, inspection teams crawl through the entire length of the tunnel, scraping out the accumulated sediment and testing each gasket with a pressurized water jet. You cannot do that during rush hour. So the tunnel is designed with bypass galleries that allow trains or vehicles to run while sections are closed. But those bypasses reduce the overall diameter. The tunnel that starts as a 12-meter bore narrows to 8 meters at the inspection zones. That is a 33% reduction in cross-section. If the tunnel was not already a flow bottleneck, it becomes one. Think about that. The tunnel is designed to protect Tokyo from earthquakes, but the very engineering that makes it earthquake-resistant creates a choke point that reduces its capacity. The more you think about it, the more the contradictions multiply. The shield tunneling method itself was pioneered in the 1800s to cross the Thames River in London. That tunnel still stands. Japan adapted the technique to operate in soft alluvium by using something called slurry pressure balance. Instead of removing the excavated material in dry form, the machine creates a slurry that becomes part of the wall. The slurry exerts counterpressure against the tunnel face. It balances the water pressure from outside. At 40 meters below central Tokyo, the tunnel passes through a layer of Tokyo gravel. That gravel is water-bearing. The shield machine must maintain exactly the right pressure. Too low, and the face collapses inward. Too high, and the ground above heaves upward, cracking roads and subway lines. The machines are equipped with hundreds of sensors that measure the pressure every 20 centimeters of advance. If the pressure deviates by more than 1%, the machine stops. The crew has to manually inject grout to stabilize the face before resuming. You want to know what keeps engineers awake at night? It is not the earthquake. It is the drill. The TBM uses a rotating cutter head with hardened steel picks that wear down against the gravel. Each pick has a lifespan of approximately 300 linear meters of cutting. The machine is advancing at a rate of 10 meters per day. Every month, the crew must replace 36 picks inside the cutter head. To access the face, they pressurize the chamber with compressed air. The air keeps the water out. The air also makes the work physically brutal. The compressed air environment causes nitrogen to dissolve into the blood. Engineers have strict limits on how long a worker can stay inside. The maximum shift is 4 hours at 2 atmospheres of pressure. Any longer, and the risk of decompression sickness spikes. There are recorded cases of tunnel workers in Japan suffering from bone necrosis after repeated exposure. The Tokyo municipal government requires full medical exams every 6 months for any worker who enters the pressurized chamber. At 65 meters, the tunnel passes directly under the Sumida River. The riverbed is only 12 meters above the tunnel crown. That is a thin roof of saturated clay. If the slurry pressure fluctuates, the river water can punch through. The tunnel boring machines have a special hood that injects a rapid-setting polymer grout into the gaps. The polymer takes effect in 12 seconds. But if the machine stops for longer than 30 seconds, the polymer expires. The entire operation is a cascade of interdependent risks. The gasket fails if the ring shifts by more than 4 millimeters. The ring shifts if the grout is injected unevenly. The grout sets incorrectly if the ambient temperature in the tunnel rises above 40 degrees, and the temperature inside the tunnel, at full depth, without ventilation, can climb to 55 degrees Celsius from the heat of the cutter head alone. You start to understand why the $12 billion figure is not an exaggeration. It is not a budget. It is a guarantee that each of those dependencies has a backup. That is the kind of thinking that separates infrastructure from infrastructure that works. Every failure mode has a countermeasure, and every countermeasure has a spare. You are already deep into this tunnel. If you want to walk the full length with the engineers, subscribe to Stay Underground, and in the comments, write Cascade. Because that is the word that defines underground engineering. Now consider the human layer. The tunnel has to be operated by people who survive the environment. The ventilation system pushes cool, filtered air through ductwork that runs the full length of the bore. At the face, the temperature is held at 30 degrees by massive cooling units that consume 5 megawatts of power. If the power fails, the temperature rises 1 degree every 90 seconds. The crew has 20 minutes to reach the exit shaft before the conditions become survivable only with breathing apparatus. The JR East records from 2005 show that the same company reinforcing Shinkansen tunnels near active faults learned hard lessons about heat management. Their tunnels cross the Itoigawa-Shizuoka tectonic line, one of the most active fault systems in Japan. The work slowed during summer months because the rock temperature at depth regularly exceeded 45 degrees. The solution was to install additional cooling plants at every 2-kilometer interval. This tunnel in Tokyo will be deeper and longer. It spans over 20 kilometers of continuous bore from Ota Ward to Edogawa Ward, passing under central Tokyo at an average depth of 50 meters. The cooling alone will cost roughly 200 billion yen over the first decade of operation. And that is before adding the cost of seismic retrofits that do not exist yet, because the tunnel does not exist yet. The budget is being revised upward before the first ring is placed. There is a quieter angle to all of this that the promotional materials do not discuss. Japan is building this tunnel because the alternatives are worse. Relocating the government functions out of Tokyo has been discussed, but never funded. The cost of moving a single ministry is estimated at 400 billion yen. The tunnel is cheap by comparison, but cheap does not mean safe. The Hyogoken Nanbu earthquake damaged tunnels that were built with older methods. The Yoshiro Review explicitly notes that those structures failed because they did not account for the plastic deformation of the ground. The modern shield tunnel with its segmental lining and flexible joints is designed to undergo plastic deformation without losing water tightness. That is the engineering breakthrough. But plastic deformation means the tunnel will be permanently deformed after a major quake. You cannot uncrack a segment. You cannot re-straighten a bent ring. After the earthquake, the tunnel will need to be excavated and replaced. The $12 billion investment is not a one-time cost. It is the first payment in a perpetual cycle of repairs. The Japanese government knows this. The engineers know it, but they have no choice. Tokyo cannot stop growing upward, and it cannot expand outward into the sea because the seawalls are $40 billion over budget. So the only direction left is down. Here is the part most people miss. The tunnel is not designed to save the structure. It is designed to save the people inside it during the 3 minutes of shaking. The tunnel will likely be damaged beyond economical repair after a magnitude 9 event. but the people will survive. The tunnel will flood. The segments will crack. The gaskets will leak, but the collapse will not happen immediately. That gives evacuation time. The same Yashiro paper that discusses the earthquake-resistant design approaches describes the importance of post-quake inspection protocols. Within 30 minutes of a tremor exceeding a certain magnitude, a fleet of ground-penetrating radar units rolls into the tunnel. They map the condition of every joint. The data is transmitted to a central command center, where engineers decide which sections to close. You want a concrete number to anchor this in reality. The seismic monitoring system installed in the tunnel will have 1,000 accelerometers. Each accelerometer records at 200 samples per second. The total data stream is 200,000 points of information per second. The tunnel essentially has a nervous system more complex than anything built in infrastructure before. But here is the irony. That system requires a fiber optic backbone that runs the length of the tunnel. If the ground shifts by more than a few centimeters, that backbone can snap. The entire monitoring system becomes useless at the moment it is needed most. Redundant radio links are being installed, but the tunnel is shielded by the ground above. Radio signals attenuate rapidly through 50 meters of saturated alluvium. The backup communication system requires intermediate relay stations every 800 meters. Those relay stations are themselves housed in reinforced concrete chambers that must survive the same earthquake. The chambers are designed with base isolation systems, the same technology used in Tokyo's skyscrapers. The chambers sit on flexible bearings that allow them to slide up to 30 centimeters in any direction. The challenge is that the utility pipes entering the chambers cannot slide. They have to bend. The bends are constructed from a proprietary alloy that can accommodate the movement without fracturing. The cost of each relay station is roughly 2 billion yen. There are 25 of them spaced along the 20-kilometer tunnel. That adds 50 billion yen to the total. You are beginning to understand why the 12 billion figure was just the starting point. And that is just the relay stations. The real number will be higher by the time the first ring is placed. This is the nature of underground work. Every solution creates a new cost. If you want to follow this project through to completion, subscribe now before the next revision comes out. And in the comments, write relay, because those 2 billion yen chambers are the nervous system of the tunnel. The tunnel will not be finished until 2039. That is a 15-year construction window, assuming no major delays from earthquakes during construction, which is already a dangerous assumption. Japan experiences a magnitude 7 event approximately once every 7 years. The Tokyo metro region has not had a direct hit since 1923. The probability of a magnitude 6.5 event within 10 kilometers of the tunnel alignment during construction is estimated at 37% by the International Seismic Engineering Institute. If a major quake hits mid-construction, the shield machine itself becomes a vulnerability. The TBM is a 5,000-ton steel cylinder partially embedded in the ground. If the surrounding soil liquefies, the TBM can sink. It can tilt. It can collapse the already built sections behind it. The insurance companies have refused to cover the construction period for exactly this reason. The risk is self-insured by the Japanese government, which means the taxpayer is not just paying for the tunnel. They are betting on it. The tunnel is a gamble on geology, on timing, on human endurance. Every ring placed is a wager that the ground will hold still long enough for the next ring to lock in. The engineers know the odds. They calculate them in the probabilistic hazard models that run on supercomputers in Tsukuba. The models say there is a 78% chance the tunnel survives the design earthquake, with a leak rate below acceptable thresholds. That leaves 22% chance it does not. 22% is not a failure mode. It is a contingency budget. The Japanese government has allocated an additional 300 billion yen in reserve, specifically for post-earthquake repairs to the tunnel during its first decade of operation. That is a separate fund, not included in the $12 billion headline. The tunnel is built with the assumption it will break. The question is how badly and how quickly it can be fixed. You are standing at the bottom of a 50-meter shaft, looking down a bore that stretches into darkness under the weight of a city. The air smells of wet concrete and hydraulic oil. The temperature is 32 degrees Celsius, even with the cooling plant running at full capacity. The walls sweat. The ground groans. The sound is low and constant, like a ship hull under pressure. This is what $12 billion buys. Not safety, not permanence. A calculated delay between the moment the earth moves and the moment the water arrives. A tunnel that learns to bend because breaking is more expensive. A city that decided the only way to survive the next earthquake was to build a path straight through the ground that will try to kill it. The shield machine advances at 10 meters per day. It will take 15 years to reach the other side. By then, the seismologists will have updated their models. The engineers will have developed new gaskets, new growing compounds, new alloys. The tunnel will be retrofitted before it is finished. That is the nature of underground infrastructure. It is never complete. It is only maintained. The last ring is placed somewhere beneath Edogawa Ward in the year 2039. The tunnel is sealed. The pumps are tested. The accelerometers go live. The city above continues its rhythm, unaware that 50 meters below, 1,000 sensors are listening for the first tremor of the next great quake. The tunnel waits. The ground beneath it waits. And somewhere in a control room in central Tokyo, an engineer stares at a screen that shows a single green line running under the city, knowing that on the day it turns red, her work truly begins.